Good morning, and thank you for attending. Today's webinar is on Method Optimization Series, Trap Selection. Jacob Redholz, our VOC Product Line Manager, will be presenting today. We will be taking questions throughout the webinar, so feel free to submit those, and we will address them at the end of the webinar. I'm going to turn it over to you, Jake.
All right, thank you. Hello, everyone, and thanks for joining us today. As Shelley mentioned, today we're going to talk about trap selection for purge and trap. But before we do that, first we're going to start with some fundamentals of purge and trap itself as a technique, and then we're going to talk about the trapping materials that are used in our analytical traps. Then we'll discuss some of the different options that we have available for our customers, and then how to choose the correct trap for your application, focusing there primarily on the EPA methods, but we'll touch on a few other methods as well. And then last but not least, we'll finish up with some tips and tricks for conditioning traps, maintaining traps, and then how to tell when it's time to replace your trap. Okay, so let's jump right in here. So what is purge and trap? Well, purge and trap is a technique that is used to improve the sensitivity of GC and the detectors associated with GCs, typically mass spec or FID, TCD, things of that nature. So purge and traps will take you beyond the sensitivity that can be reached with other traditional preparation methods, such as static headspace sampling, liquid injections, things of that nature. Okay, so a basic purge and trap consists of four main parts. The first of which, and arguably one of the most important, is the 6-port valve. So that's really the heart of the whole system. It directs all the flows through the purge and trap. So it's going to direct the purge gas that purges the sample. It's also going to direct that sample from the trap into the GC. The other important components are the sparger, or the vessel where the sample is held. So traditionally, that's a piece of glassware on the front of the instrument that will transfer a liquid sample into. But with some of the newer options available, such as the Atomx XYZ, we can actually do a purge in the sample vial itself. So we never actually have to transfer that sample. From there, it's then swept to the trap. So the analytical trap is where those compounds are concentrated before ultimately being introduced into the GC via the transfer line. Okay, so how exactly does that work though? So purge and trap works on a purge equilibrium theory, or a disequilibrium theory. So compounds of interest have to be volatile in nature, or in other words, they prefer to be in the gaseous phase. So as they migrate from the liquid phase or the solid phase, the sample that we're testing, into the gas, we sweep that gas away onto the trap, where it's then concentrated and released to the GC. So in the case of static headspace, for instance, here on the left, we can see that the sample is allowed to come to equilibrium. So the compounds of interest move from the water phase to the gas phase. And then once that equilibrium is reached, once there's no more net transfer occurring, we then take an aliquot of that headspace and then we analyze that. If we don't get enough sensitivity that way, purge and trap can improve that sensitivity by continuously replacing that headspace so that there's always a disequilibrium. There's always going to be a higher concentration in the liquid phase than there is in the gas phase. And so there's always a net movement from liquid to gas. And then again, like I mentioned, we'll collect those on a trap and then release them from the trap into the GC. Okay, so there's a whole host of parameters that can affect the efficiency of your purge and trap method. Listing out a few here would be the trap material that is used, the sample volume. So larger volumes of sample will allow for more contaminant or more target compound that can potentially be concentrated onto the trap. The purge method, so whether that's in vial or on the glassware in the traditional sense, and as far as spargers go, whether we're using a fritted sparger or a fritless sparger, all of these can contribute to the efficiency of that transfer. Same with the type of purge gas that's employed. So whether that's helium or nitrogen, and then the flow rates that are used. So either high flow rate for a short amount of time, low flow rate for a long amount of time, or high flow rate for a long amount of time. All of these things will affect the efficiency of the removal of the target compound from the sample to the trap. Now, once we have our compounds of interest on the trap, that's not the end of the things that can affect the recovery we get. Dry purge can also play a role. So dry purge is going to remove some of the moisture from that trap, but can also potentially push some of our compounds of interest out of the trap. So again, there's some opportunities for optimization there. And then last but not least, the desorb. So the amount of time we desorb for, I underscore GC flow rate here because it's the inlet flow rate of the GC that controls the flow rate through the trap, excuse me. So we want to make sure that we have enough flow through the trap to really release all of the compounds and sweep them over to the GC completely and efficiently. We also need to pay special attention to the temperatures that we use during desorb. So we want to make sure that we heat our trap high enough to release our compounds of interest, but not so high that we degrade the trap and then cause off-gassing of the trapping materials, which could introduce some contaminants into our system that we don't want to see there. So today we're going to focus specifically on trap selection. So again, like we mentioned, all the materials that are available and some of the best traps to use in specific situations. And then in later webinar series, we'll touch on some of these other parameters as well. Okay, so what are the requirements of a trap? Well, there's a couple basic things that all analytical traps need to do. First and foremost is obviously retain our analytes of interest. So if your trap is not going to trap the EPA, say 524.2 compounds, then it's not the trap you'd want to use. But we don't want a trap that traps everything. We would like our traps to exclude specifically oxygen, carbon dioxide, water vapor, things of that nature. So we want those to pass through the trap unimpeded because we don't want to introduce oxygen, carbon dioxide, or water vapor into our GC. In particular, when we're looking at mass spectrometry, we don't want to introduce those compounds. Other things our trap needs to do is release those analytes quickly and easily upon heating. So all of our traps will retain compounds of interest at room temperature, and then as they're heated, they'll release them. Our analytical traps are essentially packed GC columns, is a good way to think of them. So at room temperature, or just like capillary GC columns, compounds move very slowly through your column at room temperature, and as you ramp your oven, they start to move through more quickly. Purge and trap analytical traps work the same way. So we say that we're trapping, that we're physically stopping those compounds once they enter the trap, but that's not entirely true. They will eventually migrate through the trap under flow given enough time, but they're sufficiently retained that when we then heat and backflush the trap, we'll be able to introduce those to the GC. Some other things that we'd like our traps to do is remain stable at those temperatures that we use them, so both at a room temperature, hopefully, but also at the higher desorb temperatures. So when we heat our trap up to 250 or 260 degrees centigrade for desorb, we don't want those adsorbents to thermally degrade. We don't want them to break down, especially if they will then off-gas volatile compounds that could potentially interfere with our analysis. We also don't want our traps to serve as catalysts for reactions either with the adsorbent material itself or between other compounds of interest. So if our trap is going to facilitate reactions between, let's say, carbon tetrachloride and bromomethane, for instance, well, that would be an issue. We wouldn't want that to happen. And then last but not least, we want our traps to be reasonably priced because they don't last forever. They do eventually need to be replaced. And the best trapping material in the world, if it's too expensive to use, then it's really not a good trapping material. So there's a whole host of adsorbents that are available. They range from things such as Tenax and some natural materials such as coconut charcoal or other types of charcoal. Silica gel is a common one. And then there's some proprietary adsorbent materials, molecular sieves, carbo traps, things of that nature. Some really complex adsorbents that really do come from the GC column world. And So how do we choose? There's a lot of different options available. How do we know what's going to work best for our analysis? How do we choose a trap? Well, most of these adsorbents are going to have a relatively limited range in the compounds that they will adsorb or in the efficiency that they'll work. So 10X, for instance, is a good general purpose adsorbent, but it's going to retain certain compounds better than others. And you can run into situations where one target compound will actually push another target compound off the trap. And so you won't get a complete list of compounds that are going to be transferred to your GC. So the way we get around that is we typically use, for some of our general purpose applications, such as EPA 524 series or 8260 series, we're going to use a 3-bed adsorbent trap. And those are going to be stacked in order of weakest to strongest adsorbents, so that while we're purging those compounds that are very easily retained, that are likely to push other compounds off the adsorbent bed, will get captured by the really weak adsorbent. And then those compounds that are more difficult to retain, such as the gases, for instance, will make their way down through the bed to the strongest adsorbent where they'll be retained. And then compounds that fall somewhere in the middle usually end up in the middle of the trap. Then when we go to desorb, we'll reverse that flow through the trap so that we never push those really easily retained compounds into the really strong adsorbents. We want to make sure that everything is released completely so that we get good recoveries and we get good sensitivity on our analysis, but also it helps reduce carryover. So when those compounds, for instance, if you purge for too long or at too high of a flow rate, and you push some of those really easily captured compounds too deeply into the bed, they then linger for a very long time. So it takes many bake cycles, many adsorb cycles to heat the trap and flow enough gas through there to push those back out. And so you'll tend to see them bleed out and run after run after run as carryover. And that's obviously not what we want. Okay. So Tekmar has over 17 different trap options available that you could purchase from us. And that's a really overwhelming amount of options when it comes to which trap you want to choose for your analysis. So how do we decide what trap to use? Well, generally our traps can be broken into three main categories. We have general purpose traps. Those tend to be those 3-bed traps, and they're good for EPA methods for a long list of compounds. They're not necessarily optimized for any given compound or any given class of compounds, but they have acceptable recoveries on a wide range of compounds. And some examples of those would be our proprietary number 9 trap, or a K trap, otherwise known as a VOC 3000, traps like those. We also offer specialty traps. So these may be 1 or 2-bed traps that are optimized, or the adsorbents are selected to optimize for certain classes of compounds, such as BTEX or volatile petroleum hydrocarbons. So we offer some traps on those, and we'll talk about those here in a minute. And then last but not least, we have highly specific or very limited use traps. These tend to be single bed, for instance, like a 10X trap. Some of them may be dual bed, but they're typically used in cases where customers are looking for a specific compound, typically one that's relatively easily trapped, and we don't want to capture all the other things that might be in that sample that would really just be noise to our analysis. We can choose something like 10X, and most of those other compounds will pass through, or we'll blow them through because we need such high purge rates in order to capture our compounds of interest. A good example that comes to mind of that would be mold and odor analysis. Those are really large compounds, relatively easy to capture, hard to purge. They're difficult to get out of the liquid sample, but once they're out, they're relatively easy to capture. So we can use a 10X trap where some of those other things that might be present that we don't want to see, they'll eventually get pushed out of the trap and we won't see them. Works well for applications like that. Okay, so let's start by discussing general purpose traps. So these will be traps, like I mentioned before, that are appropriate for most major EPA methods or most major environmental methods. So drinking water, wastewater type samples, anywhere where we're looking for a really broad range of compounds. So in these cases, we're looking at 80 to 90 or more compounds. The most common traps that are used for these methods are the K-trap or the VOC 3000, our number 9 trap. Some customers will also use the VOC 4000, and the number 3 trap are sometimes commonly used. So we're going to go into a lot of detail here, a lot of data. I'm not going to belabor it here, but it will be available in this presentation afterwards, so you can dig through it a little more at your own leisure. But here's the basic breakdown of these 4 traps. So the adsorbents for each, the analytes retained. For all these traps, it's essentially everything. The only real exception to that is the VOC 4000 doesn't retain 2-cleve very well. So if you're looking for 2-chloroethyl vinyl ether, that's not going to be a good trap for you. But if that's not a compound of interest or one that's of great importance, this trap may be applicable. The other thing to note here specifically is the number 3 trap is not compatible with dry purge. So if moisture is really causing interference with your application, you need a trap that can be dry purged. You'd be looking at a number 9, a K trap, or the VOC 3000, or the 4000. Okay. So here are the GC parameters. Again, this is a very basic typical environmental analysis. So we're looking at a 20 meter 0.18 column on the GC, a typical column ramp rate, oven ramp rate, 100-to-1 split. This is pretty routine stuff for most of our applications. There's nothing special here. And these same parameters, both for the GC mass spec and for the purge and trap, were used to analyze all 4 of these traps. The only exception to that would be no dry purge on the number 3 trap because it's not really compatible with dry purge. Okay. So what are we going to look at? Comparing here across these 4 traps is the average response factor, the MDLs for all the compounds of the 8260 list. And so really we're going to break down what is the performance of each of these traps for gases, for the polar compounds, the halogens, the aromatics, and in the back end, the real heavy compounds. Okay, so looking at the gases, again, like I said, it's a lot of data, so I'm not going to really hound on the individual results. But generally speaking, the number 3 trap struggles with low-end sensitivity on the gases, and that's because of water vapor interference. So again, like I mentioned, that trap is not compatible with dry purge, so you get more moisture transferred to the GC. The number 9 trap was designed, among other things, to specifically improve the recovery of bromomethane. And so when we look at this tick in the corner here, we can see that, or excuse me, the selected ion of 94, we see that the bromomethane recovery is almost double on the number 9 trap as the other traps. We can see that, again, the number 3 trap is the lowest, and that's due to moisture interference. And in the VOC 3000 and 4000 are more or less similar on bromomethane recovery. Okay, so ketones and ethers. Again, these compounds tend to be a little more difficult, and so we see a slightly better RSD on the number 9 trap. And then again, the 4-methyl-2-pentanone is also better, in this case, on the number 3 trap. So that trap is a little more selective for that compound. And again, now we're out of that moisture range, so we're not going to see as much interference. So the number 3 trap is going to start to pick up in performance in this part of the analysis. Okay, again, halogens, we're going to see generally very similar results here. These are really typically pretty stable compounds, but we're going to see that a little better recovery of tetrachloroethylene on the number 9 trap as compared to the other traps. But this is a pretty comfortable set of compounds for all of these traps. The aromatics, again, you're going to see a similar story here. These are by far the most stable compounds, and so really all of these traps are going to perform more or less the same for aromatic compounds. And lastly, looking at the back end, again, we're going to be very similar results here because, again, these compounds are not difficult to trap. They're really easy to retain, so many traps will work well with those. The big issue with the heavy compounds tends to be more so in the carryover. So that's where we really see distinct differences and the VOC 4000 actually has quite a bit of carryover. So looking at specific carryover results here, we can see that on the 4000, we're over 1 ppb, which is kind of the limit we set for this analysis. And in fact, twice that amount on some of these compounds. Most of these compounds are close to twice that amount as compared to the other traps, which in this case we're hovering right around or a little below 1 ppb, and that's after the very first blank after 200 ppb standard. And so part of the reason for that heavy carryover on the VOC 4000 is that it tends to create a little more back pressure, so it's a little more difficult to bake that trap at high flow rates and high temperatures. You got to step back on that a little bit, and so that tends to contribute to some of that carryover issue. So just as a wrap up of these general purpose traps, we can see that all 4 traps did actually pass the 8260 MDL requirements. So if you go back and look through all that data more closely, you'll see that all of the compounds passed on all 4 traps. Each of the traps has some distinct advantages with different classes of compounds. So for instance, the number 9 and the K work really well with the gases. The VOC 4000 is not very good on the back end because of carryover issues. So for full list applications, typically most of the time you're going to go with a number 9 or a K trap, a VOC 3000. It's going to give you the best broad range recovery on all of these compounds. You're not going to have the water issues that you see with the number 3 trap because you can use dry purge on those 2. And then you're also not going to see quite as much carryover as with the VOC 4000 because we can be a little more aggressive with our bake temperatures and flow rates because we don't have some of the back pressure issues that the 4000 shows. Okay, so now let's briefly discuss some of these specialty traps. So 2 of the primary specialty traps that Tekmar offers are the number 11 trap and then the BTEX plus MTBE trap. So these are used typically for BTEX applications, gasoline range, organics, anytime you're looking at volatile petroleum hydrocarbons, those types of compounds. So here we're going to be focusing really primarily on the 11 trap, showing a little bit of data from the BTEX plus MTBE, but I mentioned the number 9 and the 3000 because, again, these compounds tend to fall in that kind of middle range. It's pretty easy for a lot of traps to do well. So even though those are general purpose traps, they still tend to work really well for BTEX and GRO type compounds. And that's because BTEX in particular, but some of the compounds that you see in GRO or VPH, some of those are in the 8260 and 524 lists. So even though these are general purpose traps, they are also good for those types of compounds because they've been selected specifically to work for some of those compounds. The BTEX plus MTBE is just optimized to also capture MTBE a little better than a strictly BTEX trap. Okay, so again, here's the GC. In this case, we used FID because this was looking at Wisconsin GRO. So here are the parameters. It was used for all the traps that the data will be presented here for. And then same with Atomx methods. All the parameters were kept the same across the various traps. So the only thing we're really changing here are the traps themselves. So we have the water parameters and the soil parameters. Any of the parameters highlighted in yellow are parameters that were not used. So for instance, the sparge vessel heater was turned off. Obviously, this is a soil sample, so we're not using the sparge vessel heater, so it's turned off. It was also turned off in the water method, I believe. Okay, so what are we actually looking at? We're going to look at calibration ranges and then whether or not each of these traps meets the Wisconsin GRO QC requirements. So if we look at the number 11 trap, we're going to see the excellent linear calibrations from 0.5 to 200 ppb. So make sure I get that right. So this trap is both in the soil mode and the water mode for GRO. It's definitely linear across a broad range. And then we can see here that we've met the Wisconsin GRO requirements. So we've got good % recoveries, and we've got good in both water, low-level soils and high-level soils or methanol extractions. So looking at the recoveries, we're very, very close to 100% recovery on 3 different sample types here. Okay, when we look at low-end detection, again, we can see that this trap has good low-end recovery on both soils and waters and methanol extractions. Again, keeping in mind that we were calibrating between 5 and 200 ppb. But if we look at an overlay of how the number 11 trap compares to the BTEX plus MTBE trap, we can see that the number 11, which is the blue, is generally a little better on some of the back end. So talking about the xylenes, the trimethylbenzenes and naphthalenes, we get a little better recovery there. On the front end, maybe just a little better on the BTEX plus MTBE trap. We're going to see a little better recovery of the fluorobenzene, the benzene, things of that nature. The number 11 trap, interestingly, actually has a little better recovery of the MTBE than the BTEX plus MTBE trap. So again, that's one of those just tricky compounds. So the number 11 trap really is a good trap for a lot of different VPH type applications. The other thing that's really nice about the number 11 trap and the BTEX plus MTBE trap in particular is that they're really deselective for methanol or for the solvents that we use. So here's a comparison of those 2 traps with, again, a general purpose trap like VOC 3000, and we can see significantly less methanol retained on those 2 traps. So this is another good example of why we have specific traps. So if we're looking for just a very small class of compounds and we want to try to reduce interference from things such as our solvent that we're making our standards with, that's where a general purpose trap is going to struggle. So the methanol is being retained here just like all the other compounds, because that's really what the VOC 3000 is designed to do, is retain everything. So just to kind of wrap that up, again, the number 11 trap really is specifically designed for this class of compounds and shows really good recoveries, low levels of contamination and carryover, and is really deselective for solvents like methanol. And again, it's very similar to the number 9 trap, just has a reduced adsorbent bed, so it doesn't capture that methanol, but is really optimized for the compounds it's been designed for. And the BTEX traps work as well, but they tend to have a slightly higher back pressure, and they also, again, capture a little more methanol, although not nearly as much as a general purpose trap. So really the number 11 or the BTEX type traps are good choices for VPH type applications. Okay, so last but not least, let's wrap up with the single bed traps. Like I mentioned at the very beginning, a good classic example of a single bed trap would be a 10X trap. And we tend to use these in situations where, like I mentioned, the number of compounds we're looking for is very small. So 1, 2, maybe 3 or 4 compounds tend to be compounds that are relatively easily trapped, but we want to eliminate everything else. So by just having one bed, we're never going to capture one type of compound. Now, the pitfall we may fall into is where there's another analyte in our sample that is more selective or more readily absorbed by the bed than our target compounds. So those analytes may push our target compounds off the trap, in which case you then may be forced to use a more general purpose trap, and then to make sure that you get a recovery of the actual target compounds, and then we can just ignore everything else, either through SIM or through the GC ramp rate to get good separation so that we can quantify our target compound. But in cases where a trap such as the 10X will work, it makes for a really good option. You really eliminate a lot of the other compounds that may or may not be there. Some of the drawbacks to using 10X in particular is that it tends to have a really high back pressure. In fact, some of those other traps that we've mentioned that have high back pressures, you'll tend to notice that they also use 10X as one of their beds, and that's what's really driving that back pressure. Other issues with 10X is, as it's heated, it can tend to outgas benzene, toluene, and ethylbenzene. So again, if those are target compounds such as a BTEX application, a strictly 10x trap is probably not going to be the best choice. Although a lot of that outgassing can be taken care of through trap conditioning, but it still tends to linger on longer than most people would like to see. Okay, but a good classic example for 10x would be mold and odor analysis. Like I mentioned, these are really big compounds, really easy to trap, can be somewhat difficult to release from the adsorbent, also really difficult to get out of solution. So we tend to purge really aggressively to get these compounds out of solution and onto the trap. And then, so something like 10x tends to not retain them too strongly, so we can then desorb them into the GC, and we can really clean those traps up between analyses. We always recommend the number 1A trap, which is a slightly larger adsorbent bead, and so that really helps improve the back pressure because the trap doesn't pack quite as tightly. It increases the trap life because it doesn't break down quite as poorly, and it doesn't clog. Again, like I mentioned, these compounds are really large compounds. So when any of them that do get retained in the trap and don't get baked out, they can tend to cause back pressure as well. So using that larger bead size really helps reduce those problems. So here we're looking at, again, a 20 meter 0.18 column. We're doing a mass spec analysis of these compounds. Pretty routine stuff. The one big thing I'll point out here is that we have a relatively low split ratio. So again, we want to try to get good sensitivity because these are such poor purgers. So with this method, we're really looking at a low split ratio. We want to transfer as much of these compounds from the trap to the GC as possible. And they tend to be well outside of the waterfront. So we don't really need the split as a moisture control in this type of analysis. We are dumping a little more water into the GC in the mass spec than normal, and that may cause some slight increases in like source cleaning, things of that nature, but it's not going to cause a direct interference with our target compounds. So here's the Atomx method parameters. You'll notice here that we're also using a longer desorb time, so in this case 4 minutes, and that's really because of that low split flow. We want to make sure that we get adequate flow through the trap to get adequate desorption. So we'll run that a little longer. And again, like I mentioned, moisture is not really a concern here for us, so we can suffer that longer desorb time. You'll also notice here that we have a pretty aggressive purge settings of 10 minutes at 100 mils per minute. That's really aggressive, but again, these compounds are very difficult to get out of solution, and they tend to stick to the 10x really, really well, so we don't have concerns of pushing them through the trap and out the vent. Okay, so looking at some calibration results here, we're going to see that we have really nice calibrations, whether we look at these from an average response factor or a linear calibration. Really, really stable across a broad range and relatively little carryover. And that's, again, due to a good aggressive bake out between samples to get the trap cleaned up. So we can see here from 1 to 100 ppt linear, this is using SIM, but good recoveries, and that's in large in part thanks to that trap. So it's not retaining other things that are going to interfere with our analysis. So just to wrap up single bed traps, they're nice because we can choose the adsorbent based on the compounds of interest we're looking for. So we can choose some really exotic beds potentially that will really specifically trap one type of compound, or we can choose 10x, for instance, as a relatively general purpose adsorbent, but by not including other adsorbents of varying strengths, we can really exclude a lot of compounds from being trapped. But because of that, they're not nearly as versatile as multi-bed traps. So if we're looking at 5 or 10 different compounds, that's where you might start moving into a multi-bed trap. Definitely like, for instance, the VPH, the BTEX. There's not a lot of compounds there, but a multi-bed trap tends to do a little better than a single bed trap, such as a 10x. Okay, so now that we've talked about how to choose your trap and what types of traps tend to work best for which types of analyses, now let's talk about how do we care for our traps, how do we maintain our traps, and how do we know when to replace our traps. We offer a really wonderful VOC reference guide. You can go to our website and request it to be mailed to you, or I think we also offer it as a download. And among other things, this poster has a section on traps. So it talks about all the different traps that we offer, recommended bake pressures, recommended bake flow rates, times, temperatures, things of that nature. And so you really do want to adhere to those recommendations. When all of our traps ship, they come with a sheet in there that details out those parameters. So when you condition, what temperature and flow rate you should use. When you bake the cleanup between samples, what temperature and flow rate, and then also the desorb temperatures that you should be using. And I caution you here that the defaults in our method, so like the Atomx XYZ method or the Lumen method, is not necessarily going to be correct for the trap you're using. So those defaults are really set based more on the general purpose traps, such as a K trap or number 9. So if you're using one of these other specific traps, you'll want to definitely reference either the poster or the piece of paper that comes with your trap, or you can always call our technical support center to get guidance on that. But definitely make sure that you adjust your method parameters to match what the trap needs. Don't necessarily assume that the default is going to be appropriate or adequate. Okay, so we always want to condition a trap. Anytime you install a brand new trap, you're going to want to condition it because they do off-gas. Every time they get heated up, they're going to off-gas some compounds. The adsorbents, by their very nature, they are organic compounds. So they will break down, they will release some volatiles. So the way we typically do that is we can go straight to bake. So our software offers a bake button. So if we're talking about the first generation Atomx or the Stratum, so the older TechLink, you're going to have a quick button up in the menu. You click that button, it's going to pop up a window where we can select the flow rate, the bake temperature, and the amount of time you want to bake for. Again, the recommendation for the number 9 in the K trap is 270 degrees for 120 minutes, but that's going to be specific to each trap, so you want to look up that information. If you're working in the newer TechLink, simply click the Tools button, and then under the Commands column, there's a Bake button. Again, when you click that button, you'll get the similar window where you'll choose your flow rate, your temperature, and the amount of time you want to bake for. So always start with conditioning your traps, and then, of course, always make sure you do a leak check after installing a new trap to make sure that it's installed properly and there are no leaks in the system. Beyond that, really, maintenance of traps just comes down to using adequate and correct bake measures. So you want to make sure that you use a flow rate that's going to be appropriate. In most cases, we really don't want to flow much above 200 to 300 mils per minute. You get up much higher than that, and it's going to put quite a bit of stress on your trap. All of our traps will handle the full 500 mils per minute that our mass flow controller is capable of. But as you go more and more heat cycles and higher flow rates, that generates more pressure. That's all going to lead to the breakdown of the adsorbent beads. So keeping those flow rates reasonable, I think 200 to 300 mils is certainly reasonable for most applications, and keeping those bake temperatures reasonable, staying within those recommended limits, are really going to help elongate the lifespan of your trap. The flip side of that is you do definitely want to make sure that the cleanup is obviously effective. So if you're not baking hot enough or not flowing enough flow or not doing it for long enough and you have carryover, well, then that trap's not being, it's not performing at its best for you either. So we want to make sure that we choose parameters that are good enough to get the cleanliness we need, but not overly aggressive and lead to premature trap wear out. So how do you know when to replace your trap? Well, the simple answer is replace it as often as needed, but that's not really a very helpful answer. So what we can do is you could put your traps on a routine schedule, like every 2 months I'm going to install a new trap, but that likely would mean that oftentimes you're throwing away traps that have quite a bit of service life left to them. So there's really two main ways that we can track trap performance and decide when it's time to replace our trap, rather than just waiting until we start to see failures and, oh shoot, now we have to because our application isn't working anymore. So the first of those two ways would be to watch indicator compounds. So some of those trickier compounds, like the halogenated compounds, in particular chlorinated compounds, tend to decrease as the traps break down. So Bromoform is another one that is really a classic. When you start to see your bromoform calibration fall out or your check standard fall out, that's often a sign that your trap needs to be replaced. So a fresh trap can bring that compound right back up where you expect to see it. You get your low-end sensitivity back. It's a good indicator. You start those tricky compounds start to struggle, it's not going to be too much longer before your really stable compounds also start to struggle. And you really don't want to wait till you get to a point where you're failing calibrations and you can't run samples. So indicator compounds can be a good way to determine when to replace the trap. The other good way to decide when a trap has reached its end of life is by checking the bake pressure. So again, like I mentioned, as we start to add heating and cooling cycles, we break down those adsorbent beads. As they break down, they get a little smaller, they become less efficient, and they can tend to cause, they pack tighter in the trap and can cause back pressure. And then eventually, if it gets bad enough, the flow rate through the trap will blow channels, and you'll get channelizing through your trap. And so really what that means is that you'll have much less of your trap being exposed to your sample because your sample is taking a preferential pathway through the trap. So then it becomes much less effective. So the way we can avoid all of that is looking at our bake pressures. So we can go into the help file, or the history file, excuse me, of the TechLink, filter by bake pressure, and you'll see all of the bake pressures for all of the samples that have been run. And what we're looking for is a significant jump in that pressure. And so what that's telling you is that your breakdown has reached a point where you've really started to generate back pressure based on breakdown, not simply based on the qualities of that particular trap. So you'll typically see a jump of 20 to 30 psi in a span of just a couple samples, like 5 to 10 samples. So traps such as the number 9 or the K trap tend to have bake pressures somewhere in the neighborhood of 10 to 15, maybe 20 psi typically. If those jump up to 30 or 40, 40 is really starting to push the OPL, or the overpressure limit of the system. But when you see that significant jump up to the 20 to 30 psi range, that's going to tell you that that trap's broken down. You can also see a similar trend in the purge pressure. So purge back pressure tends to be somewhere in the 5 psi range. When that jumps up to 10, 15 psi, that's a real good indicator that your trap is very short in life. It's not going to last much longer. So by either looking at your indicator compounds or looking at your bake pressures, it'll allow you to replace a trap before it fails. So there's no reason to wait until it's no good. We can really be much smarter about those trap replacements. And it helps keep costs down ultimately because you're not throwing away traps that are still good and still have serviceable life. You're not making guesses on when you'll need maintenance. You can really watch these compounds over time, and you really can predict when your trap's going to go bad. So you can choose a good day to shut down and make that change instead of coming in one day and going, oh man, we're not running today. It really cuts out those types of surprises. All right, so speaking of traps, I'd like to mention that we now have a new online store. So all the traps that I've mentioned today, plus all of the other myriad of traps we offer, are on our online store, so you can go there to check them out. There's pictures of all of our spare parts and the part numbers. So even if you're not sure exactly what you need, you can compare pictures. If you're still not really sure, you can go armed with part numbers when you reach out to the technical support folks to help get resolution for any issues you may have. Currently, we can only ship to domestic customers, but again, this is a great, excellent resource for anyone to go check out the actual photos of spare parts to compare what you think you need versus what you're ordering. Just a really great resource that's available. All right. And so just like take a moment to thank everyone for attending today. And with that, we'll go to questions.